Welcome to the grand tour through the thin film deposition and analytical facilities here at the Institute for Materials Physics. At first I'm going to focus on the deposition side, namely the sputtering and the pulsed laser deposition, and afterwards I will show you some pictures of our X-ray facilities. We have quite a bunch, I'd say. And afterwards some materials properties or characterization units we will also have a look at. So at first the sputtering techniques. Here on the second floor we have two ion beam facilities. The sources are from IonTech, or they are IonTech compatible, and we have dual beam capabilities, and meaning that we have ion beam assisted deposition. We have UHV chambers, of course, with large pump systems. Here you have that very large pump on the right-hand side of, or the left-hand side of the machine, the right picture here. And we can have high temperature deposition and also reactive sputtering. With those machines we have sputtering powers up to 30 watts, and we have the opportunity of having in situ target exchange up to 3 targets, and also in situ measurements are possible, for example stress or read. The other facility is a magnetron diode sputtering machine, and we have here sources from angstrom up to 3HF or DC sources. And they are more powerful, namely 500 to 1000 watts. Also this is an HV chamber, and high pressure, high temperature deposition is possible, as well as reactive sputtering. If you have some questions to that machines, I'd like to refer to you to Jörg Hoffmann. The next thing where I am in charge of is the PLD setup. Here we have the laser and 3 deposition chambers. From the top it looks like this. We have directly behind the laser exit we have an attenuation system where we can attenuate our laser beam in many steps, from 97% through passing to 0, I would say. And we have different mirror systems where we can then guide the beam through one of our deposition chambers. At every deposition chamber we have the possibility of monitoring the energy, and we have a lens installed there. We can focus the laser beam onto our targets. What is in general interesting about these setups, we have some automated functions. We have an interlock system, meaning when one of those boxes here, those aluminum boxes like this one here, is opened, we have a switch that is directly connected to a lamp that's outside the lab at the door. And if we are operating in this open beam mode and the door of the lab is opened, then the shutter of the attenuation system is automatically closed to prevent the radiation of people without the protection glasses. So this is equipped with the complete setups, and we have a lot of motorization on the different deposition chambers, and all those motorizations are also equipped with end switches. So the for example the height of the target or the rotation position of the target is only possible within certain limits. We have, for example, also the lenses are all movable and they can rotating, meaning that we have variable focus sizes or energy densities. The protective screens you will see in the other video that are installed for our chambers. The energy density measurement I already mentioned, and we have an automated target movement that is continuously during the whole PLD process. As I said, the motorization is installed, or many motorization possibilities are installed with the chambers. We have also a control unit, a PC that's equipped with a Labview program that is written by one of the doctoral students of Hans-Ulrich Krebs, who was in charge of the PLD system in the past, and he also installed this PLD system. I think it was in the beginning of the 90s where he started this PLD group here in Göttingen. And yeah, this self-written code, at the moment it's in German, but it's also one of our goals to transfer this to English. You can control the system then here with a joystick. That's quite fancy. And it's possible to have some automated calibration, so that you're telling the system what flux you need, and then the attenuation system is automatically adjusted to that value. And during the deposition, the energy of the laser beam, there is an energy monitor, of course, in the laser system. This is recorded and stored during each process. Yeah, this whole setup is a little complicated, but everything I know about this setup is stored in the wiki of the institute. Again, in German still, but I'm working on having that in English. So now I'm going to talk about the different chambers. The chamber 1. At the moment we have here halides and polymers, or everything that does not require such good vacuum in the background. We have here a load lock system and a target holder. There's an active site of about 8 times 1 centimeter where you can deposit your target on. And we have here a substrate that can be introduced here with a diameter maximum of 2.4 centimeters. This is a round substrate holder, and we have the opportunity to have here a ring oven for the substrates, heating up the growing layer of about 800 degrees C. We can install gas flow, and also vaporization of alcohols or water is possible, and we can also have resistivity measurement in this chamber, where you have here one of the holders. Here it's installed in the chamber. Here in the foreground you see this 8 by 1 centimeter active area for the PLD system. So the laser would come from the top left, shining on here onto this target, depositing here then through this mask. The next chamber, the chamber number 2, where we grow our oxides or complex oxides on, is at the moment under construction. But what we planned I will show you here. We have a complete new chamber where we will have also an in situ ellipsometry, as the guys from the MID system already have. So we try to copy that system to our facility, since the results of the ellipsometer controlled layers are really impressive. And what's special about, well, what will be special about this system is that we have the substrate coming here from the top. This is then irradiated with the ellipsometer laser here, and the target is at this position. We have also here several targets that are hit then by the incident coherent laser. So the plasma plume is spreading out in the horizontal direction, and we have we try to get rid of the problem of the exfoliations and the droplets, since we have the substrate here in this off-axis position. It will in the future also be possible to rotate that substrate, so you have then homogeneous and hopefully droplet and exfoliation free high quality layers. We will have 2 targets in this facility here, and the substrates that will be the standard 10 by 10 or 5 by 5 substrate. We are clamming them, and we will clamp them to our substrate heating system that's capable of heating the substrate up to 1300 degrees C. We will also have, since we're growing oxide, the opportunity of having gas flow inside that chamber. And yes, I just told you we have the off-axis deposition and in situ ellipsometry. The last of the chambers that are currently installed, chamber 3, there we have the best background pressure. If on good days, I would say, we can reach 10 to the minus 4 millibar before the deposition procedure. Yeah, we are quite proud of that. And here we have 3 targets in parallel in the deposition chamber, and the substrate are again round, 2.5 centimeter coarsely in diameter. And we have a load lock. You will see in the other video then look into this load lock here, where we have several spots for targets and substrates, so you can exchange your substrate or even the targets during the deposition without breaking the vacuum. We have also a rate monitor installed here in that chamber so that you can check your deposition rate also in situ during the deposition. What we furthermore have, this is an old picture of the chamber number 2 that's currently then out of order, and we have also other spare chambers. And what we have still in the shelves is a mass spectrometer, an Auger system, and a Reed system. But to be honest, this the status or the condition of those 3 parts is unknown. So yeah, if you are having a lot of free time, you can then try to rebuild all of those systems. Yeah, this was the part for the deposition. Now I'm showing you our X-ray facilities. We have full and basic facilities. At first we have a Bruker and a Philips machine. Here we have a copper source. Here we have a cobalt source. All are equipped with different numbers of goniometers, so here both 4. What's special about this Philips Expert system is that we have a hot stage that's also shown here on the right hand side. There we have the cobalt source, and here this special system here is then this dome-shaped hot stage. Now it's heated, so it's glowing red, and we can reach temperatures up to 900 degrees C, and we can do then in situ analysis under air, argon, or even vacuum. What we additionally have, 2 other full protection systems, here the Siemens and the Bruker Apex, a chromium source and a molybdenum source, and with this Apex facility we also have a cooling stage that's operating at liquid nitrogen temperature. That's quite special. The high and basic protection facilities are Seifert and also Philips facilities, where we have cobalt source and copper source. So if the other facilities are highly booked, you can also have this more simpler but also capable of doing quite nice scans machines. Some materials response characteristic machines are listed here. Here we only have the most important machines. Of course, we have also other facilities like ovens or light microscopes or scales or something. So we have everything to manufacture the targets for the sputtering and the PLD systems ourselves. We're doing that especially for the complex oxides. But what we have here now are very nice machines. We have an ex situ ellipsometry system, and with this you can estimate either the thickness or the optical properties of your material if you know the other one. We have here thermogravimetry or differential scanning calorimetry, so you can measure the change of mass or heat when the temperature of your sample is raised, and with that you can detect, for example, phase transitions. For the mechanical properties, we have different indentation systems ranging from the nanoscale to the micron scale. We have here a self-constructed 3 omega measurement system, that is to estimate the conductivity of your thin films. And here we have the Fourier transform infrared spectroscopy. There you can measure the absorption edges in your sample, in this region here. For thin films, you can also have this in transmission and reflection if you want to estimate the bulk values, for example. The next thing we want to stress here a little more in detail, we have here low temperature electric characterization facilities. The first one is for fast electric characterization, and here we have a closed cycle cooling system, and electric characterization down to 30K is possible, and it can be equipped with different measurement techniques. The other thing is here a photoelectric characterization unit, where we also have closed cycle cooling system, and the characterization is even down to helium temperature it's possible. And what we have here also, we have mono and polychromatic illumination by one of the lamps, and we quite newly installed have also a laser system in here. And what is also accessible through the collaboration to the first physical institute, we have here a PPMS, so a physical property measurement system, where we can also cool the temperature to temperatures of liquid helium, and we can apply strong magnetic fields. The next thing we have here in the Institute of Materials Physics is a laser-supported tomographic atom probe. So you shine a laser on your sample that has to be in the shape of a tip. You can cut that down with an FIB system. We have actually two here in the institute for cutting our samples, for example. And since they are so highly booked, we have two of them, And here with that laser tap, we have the opportunity then to reconstruct by evaporating the tip with a laser and recording the ions at a screen to reconstruct in 3D the samples with atomic resolution. The next thing here, we have an atomic force microscope from Asylum research, with different kinds of tips, and quite fresh. We have here also an XPS system that was installed in the last year, if I'm correct. And this is then opening up also the path to the electron microscopes, but this will be the topic of the presentation of Tobias. Thank you for your attention.